The following program is brought to you by Caltech.
All right, I'd like to go ahead and get started again if people want to take their seats. So now we're going to switch over to this other topic, which I mentioned is an exciting area in planetary science, and that is the field of extrasolar planets. And our first speaker is an assistant professor of astronomy. It's Greg Hallinan, and he's going to talk about looking for a pulse, the search for radio waves from extrasolar planets.
Okay, thank you, Ken, for having me here, and Dave Stevenson and all my GPS colleagues for actually bringing me along here today. It's been pretty inspirational so far. It's kind of a hard act to follow. Okay, I'm here to talk about extrasolar planets moving away from our own solar system, and specifically radio waves from other planets. First off, very briefly, I want to mention that I'm here talking today, but a lot of the work is done by my group, postdocs and students who are today working, for the most part. One's in the audience. But they're the ones who are on the ground doing a lot of the hard work, and I want to just acknowledge them first. All right, so I'm interested in how stars and planets interact, and more specifically, how magnetic fields possessed by both play a role in the habitability of a planet. We live with a star, and that star is active. It has magnetic fields. The magnetic fields give us the sunspots we're familiar with in the optical, but at higher energies we see that you have a lot of high energy particles, produce a lot of UV radiation, X-ray radiation. You have reconnection of magnetic fields that accelerates particles to very high energies, and these sometimes get thrown out towards the planets that orbit it. And here we have, as we're seeing, for example, streamers, and eventually we zoom out here, we see some of these coronal mass ejections as they travel out and disturb the interplanetary medium. So this activity very much dominates our local space weather, and we can see that actually in the next slide, where we track an animation of what a CME impacts the Earth-space environment. Here's an example of a flare-driven CME, a shock wave of material and magnetic fields that are thrown out into the solar wind and out towards, in this case, Earth. Happily, the Earth has its own magnetic field, which acts as a shield. And that shields us from a lot of the high energy and particle flux associated with that event. And what we have is the material accelerates down towards the poles, and we have the beautiful aurora. Shown here from a different perspective, but a beautiful phenomenon, but it just tells us that we're in the middle of a very large geomagnetic storm. And that storm affects us in many ways. You have a few minutes after the event, the light travel time, you have a large amount of X-ray and UV radiation that basically heats the Earth's ionosphere, and that can affect communications, satellite communications, and so on. And then thereafter, you have the particle flux eventually and the magnetic flux impacting the Earth's local space environment. And that has a tremendous effect. That can affect navigation. It can actually, in extreme events, affect power grids. And of course, we have aurora. So it does very much dominate our space environment. There have been examples in the past where there have been damage to the power grid by very large events. Here's one, for example, that in 1989 damaged took out most of the northeastern seaboard temporarily. And this kind of activity obviously is on a cycle. In the solar case, every 11 years we have peak in activity, large number of flares, larger number of CMEs, and we're just coming out of that peak right now. So moving on, what we're really interested in doing in my group is looking at how this kind of interaction occurs for other stars and planets. And the last 20 years has been a very rich period. We now know, as of this morning, of 765 confirmed extrasolar planets, and more than 3,000 candidates, largely in the latter case due to Kepler, a fantastic mission that's been doing great science the last few years. So we're out of the era now, at this stage, we're very firmly in the era of discovery, and we're actually moving to the era of characterization. And Heather will give a much more in-depth talk of how we characterize these kind of planets. The question I want to ask is, how does the activity of the host star and how do the magnetic fields of the planet play a role in defining whether those planets can host life? Can we directly detect the flares, the CMEs? Can we detect the aurora and other sorts of triggers that tell us that these planets have magnetic fields that protect them from their stars' heightened activity? And what we primarily use in my group is radio observations. And it turns out that radio observations are a very powerful tool of this kind of activity. Radio observations trace particle acceleration. And as you can see from earlier slides, These are very dynamic environments, a lot of material being accelerated to high energies, and that gives us a lot of traces to follow. Specifically, we're lucky in Caltech. Mike mentioned how many resources we have and how many telescopes we're involved with. We certainly have the world's premier university radio observatory about 4 hours drive north of here. And that's the Owens Valley Radio Observatory. And here's a photograph of one of the large dishes that exist on that site. We've got a number of facilities operating over a wide range of frequencies. I mentioned some here: Karma, LWA, Starburst, Owens Valley Solar Array. These cover 4 orders of magnitude in frequency. It's probably a bit more of a breadth in frequency than any other observatory on the planet. And by having all these projects on site together, including very large ones like Karma, which is a sub-millimeter array, it means you've got a lot of people on site with a lot of expertise and a lot of resources that are shared, and it really enables unique science that you can't try and do anywhere else. And I'll describe some of that. I'm primarily focusing on 2 experiments that we have at the observatory, one of which is the long wavelength array and Starburst, that are built to try and track the activity of stars and their planets and how they interact. First off is the Starburst program. That is a program that will try and detect and image those kind of shock waves, the CMEs produced by nearby stars. And it's actually a project worked on by a student of mine, Jackie Willitson. As a starting point, I'll give you a quick tour of what kind of radio emission you get from a star. First of all, the sun produces radio waves just associated with its thermal atmosphere. It's surrounded by a chromosphere and corona that's heated by the underlying magnetic field. The temperature is up to 10 to 6 Kelvin. Associated with that thermal plasma, you have radio waves at very low frequencies. But they're quite faint. But the sun is a very inactive star, and typically that's all you would detect in the radio. However, when the sun is flaring, you have much more intense, much brighter emission. And here I'm showing an example of what happens when you have a flare or shock wave, in this case, a CME eject. We see this kind of behavior in time and frequency space. Here's my one plot, essentially. Here's frequency and here's time. What happens, you have this very, very intense radiation that travels across this plot in a very distinctive fashion that tells us about the density of the plasma at the site. It tells us about the velocity of the plasmoid traveling outwards. And it's a real signature of there being a shock wave, a CME, being sent from the sun. And we've been detecting these from the sun for 70 years. The very early days of radio astronomy very much focus on this kind of activity. So what can we detect from other stars? Can we detect the quiet sun, for example? Well, like I mentioned, it's quite faint. And it's only been in the last year we've managed to get a detection for the first time of a quiet star that's the same as our sun. These are observations done in the last year by a student of mine, Jackie Willitson, where we looked at very, very similar stars to the sun. These are Tau Ceti, Eta Cas, and Forta Eridani, the nearest K and G dwarfs within 20 light years. Very, very faint. It took a lot of observing time with a very, very large telescope. In this case, the Very Large Array in New Mexico that just had a very substantial upgrade to finally get sufficient sensitivity to detect a sun-like star as a quiet star. As it happens, because of the very nearby G dwarfs, these are also very often the mainstays of science fiction. And one of these objects here is the host star for Vulcan. So we can say we've got radio waves from Vulcan in the last year. That's an example of one kind of emission we get from nearby stars. But and during flares, solar-like stars are more active. But as it turns out, the sun is a very quiet star, luckily for us. A lot of stars are much more active and they flare much more often with much more intensity. And in fact, our sun, as a younger star, was much more active. So young stars tend to be a lot more active. And another class of star that's very active are M dwarfs. M dwarfs are the dominant stars in our galaxy. 95% of stars that can host evolved exoplanets, that's those that have ages greater than a gigayear, are M dwarfs. They're the smallest runts of the litter in our galaxy, but they're very, very populous. Kepler has shown that low-mass planets are very frequent around such M dwarfs, and they're becoming an increasingly important class of planet for discovery and follow-up. Likely the nearest habitable planet will orbit an M dwarf. However, M dwarfs are much more active for much longer than stars like the sun. They flare intensely, and sometimes up 10 to the 4 times more than the largest solar flares. And of course, they're much cooler and fainter than our sun. Therefore, the habitable zone is much closer. So you're getting bad and a lot of radiation. And these are that means higher X-ray flux and UV flux. That enables photochemical reactions that can lead to atmospheric loss. And then you have the particles. You have the ejected particle emission that can basically also, in a different fashion, erode the atmosphere. So you have these two phenomena that are basically potentially causing problems for atmospheric retention. We have a program at Owens Valley called the Starburst Program. This program, just funded by NSF for construction, will build dedicated hardware that would connect these two dishes that have been on site at Owens Valley since 1955 to look at nearby stars. Happily, I mentioned having lots of experiments on the ground enables a lot of other science. These two dishes are used during the day as part of the solar array that monitors the sun every day. And over the last 2 years, I've had a major upgrade. Now, at nighttime, where happily the sun is not up at night, happily we can use those two dishes to look for the same kind of activity from nearby stars. And that's what we're focusing on over the next 2 years, is trying to image and detect the same kind of events from the sun for nearby stars. So this is actually began construction, and over the next 2.5 years, when it's finished construction, we will get about 7,000 hours on nearby stars. Here's an example of one kind of event we've detected with the pilot survey using the VLA. And we already see that we can get very easily very bright kind of bursts. And this is actually the first broadband burst ever detected from an M dwarf of this nature. And I zoom in here and show you all the structure we see associated with that shock wave traveling within that star's magnetosphere. Starburst will allow us to track the entire event all at once, because the key part of the hardware we're building is a wideband system that allows us to measure the entire event all at once. And here's how Starburst will function. We will have our radio dishes and a small optical telescope monitoring nearby stars. That tells us when we have a flare, we'll see an optical flash. And more importantly, we'll see the shock wave that may be associated with such an event that will look kind of like a stellar burst. What happens next? That tells us we're seeing a flare and potentially a CME on a nearby star. We trigger what's known as the VLBA, 10 very large dishes distributed right across the United States that operate at gigahertz frequencies. One actually happens to be in Owens Valley, this dish right here. That allows us to make an image, the highest resolution image achievable with any telescope, of that CME as it happens. This image right here is an image of a small M dwarf during a CME. It's the same M dwarf I showed in the previous slide having a burst. This little kind of disk right here corresponds to the size of the star. We're seeing this kind of outflow structure associated with that star during a flare. What we're going to do is detect those in near real time and then map those events back towards the magnetic field of the star. So the sun's magnetic field is very different from those of M dwarfs. And that's a very key point. The sun's magnetic field has high strength, it bursts through near the equator. These stars have very large kind of dipolar fields, very different. And how they interact with CMEs could be very important for defining what kind of geomagnetic storm their orbiting planets could be bathed in. For example, you see here you have this kind of closed field lines, dipolar structure. As it turns out, if you map this kind of ejection to the star's magnetic field, it looks like it's actually traveling up and down the poles, away from where you expect it to cause trouble for an orbiting planet. That basically is the Starburst program that's just starting right now. We'll try and trace this activity for nearby stars and planets. The other project is called the Owens Valley LWA. And that's going to actually try and detect radio emission from the planet itself. So I mentioned that the sun's a bright radio source. It turns out so are planets. And I'll go right back to the start of when we understood that planets became radio sources. It's the mid-50s, and 2 astronomers built an array in Maryland trying to detect our image, crudely image extragalactic sources. This is the very early days of radio astronomy. And they noticed a very bright bursting source in their data. It had been the early days of radio astronomy. It wasn't very clear. The systematics weren't very well understood. Initially, the 2 gentlemen in question were questioning whether it was a farmhand traveling home in his tractor, just basically the tractor sparking and causing this kind of problem. But after a few days, they realized this source was moving on the sky as an astronomical source, moving sidereally. They knew it was non-terrestrial. And eventually they figured out that in that direction of the sky was Jupiter. And that was a very important discovery. That was the first time it was confirmed that Jupiter had a magnetic field. We knew Earth had, but we didn't know that Jupiter had. This is pre the space age, remember. This is very, very early days for planetary magnetospheric physics. It firmly established the rotation rate for Jupiter. Jupiter's cloud bands rotate at different rates, but the magnetic field is anchored to the core. And that established very clearly that Jupiter had a specific rotation period. And probably most importantly, the radio emission is produced at a very specific frequency that tells you how strong the planet's magnetic field is. And in the case of Jupiter, it's extremely bright below 40 megahertz. It's actually as bright or brighter than the sun in the sky very often. And beyond 40 megahertz, it disappears, because that corresponds to the surface magnetic field strength level. And that's how we could first track that phenomenon for Jupiter. Last point, I show here a kind of cone emitting from that area. The radio emission is very narrowly beamed, like a lighthouse. So every 9 or 10 hours, you have this flash of radiation as that lighthouse beam sweeps Earth. And that's how we know that it's got a specific rotation period. It was afterwards established that Earth also has very strong radio emissions. This wasn't discovered until the space stage because our ionosphere blocks the radiation. The radio emission from Earth is too low frequency. But once again, this movie you've already seen explains where that radio emission comes from. It's associated with the aurora. Those electrons that travel down and collisionally ionize and excite with nitrogen and oxygen produce extremely bright radio waves, intensely bright radio waves, 10,000 times brighter than anything we produce on the ground. And as it happens, every planet in our solar system that has a magnetic field produces this very bright radio emission. And that was another one of the beautiful things that Voyager was able to discover. It actually measured the radio emission from Saturn, Uranus, and Neptune for the first time. So, can we detect this kind of radio wave from other planets? Well, Jupiter is intensely bright. I mentioned that sometimes it outshines the sun at low frequencies. If you put Jupiter at the nearest star, just the vast distance in space, it's incredibly faint. You need a huge amount of collecting area to get a detection. So what can we detect? Well, first of all, it's important to highlight that going after exoplanets in the radio is a very worthwhile pursuit, because it tells us whether or not planets have magnetic fields, and allows us to constrain what governs the field strengths and topology of fields for planets. And eventually, we should be able to infer whether habitable planets have magnetic fields that can protect their biospheres. So how bright a planet is in the radio is a function of how close it is to its parent star, because it's actually the stellar wind that's powering the emission. So if you want to have a bright planet in the radio, it has to be pretty large and pretty close to its parent star. Happily, there's a whole population of those that were unexpectedly discovered called hot Jupiters, and they're the ones we're going to try and detect first. They would be up to 10 to the 5 times brighter than Jupiter, and hopefully detectable at low frequencies. There have been efforts the last 30 years to try and detect this kind of emission, and unfortunately no detection so far. However, I think we're entering the era where that's going to be possible, and there's other influences that suggest it is possible. One is a phenomenon associated with objects called brown dwarfs. These occupy the mass gap between stars and planets. They're too small to sustain nuclear hydrogen burning at their core, and they're too large to be planets. And they're basically one of the most populous members of our galaxy. Less than stars, but still quite a large fraction. As it turns out, you may have to ask the question, do brown dwarfs behave like stars with star spots and flares and corona, or do they behave like planets with large-scale magnetic fields and aurora? And as it turns out, brown dwarfs have aurora. Here is an image. At the time, this was the deepest radio image ever taken with any telescope, which shows a brown dwarf. And it pulses, just like Jupiter. And that confirms for us that these things behave exactly like planets. And in fact, most recently with the Keck telescope, we've also confirmed that these brown dwarfs have optical aurora. So how they behave like giant planets rather than small stars. But that tells us this kind of behavior, this kind of emission, can be detectable at great distances. And as it turns out, this kind of really revolutionized our understanding of how strong fields are for these kind of objects. So there have been lots of attempts to try and detect planets with the radio. And here's one of my own observations, taken with a very large telescope in India called the GMRT, the Giant Medium Wave Radio Telescope. We want to go to long wavelengths and low frequencies to detect the emission. And once again, we're looking at a hot Jupiter here. And I've drawn on the constellation just to kind of indicate where this particular star is that hosts this planet. Talbot is one of the most well-known hot Jupiters. I show here a lower limit on its mass. That's actually now being much more well-constrained. It's very close to its parent star, 20 times more close than Earth to its parent star. And it's very close by at only 50 light years. It orbits its star every 79.5 years. However, it's so close to its parent star that it has become tidally locked. Therefore, its day is also 80 hours. If we want to get the pulse from a planet, we've got to observe for very long periods of time. And it's very difficult to go to a telescope and say, can I please have your telescope and observe that part of the sky for 100 hours where I might not see anything, please. And that's been a very difficult process, but we've done that on many occasions. This is an example of one observation. Here is the image associated with that observation. Here's where the planet is, no detection. Here's the time series, and we've got no pulse. So this is one of the hardest constraints ever produced for a planet, but it's still nowhere where we need to be. We're not at low enough frequencies. This is at 150 megahertz. Remember, Jupiter drops off exactly 40 megahertz. It's gone. Also, remember that these things are beaming like lighthouses. If you're looking in the wrong direction, from the wrong direction, you can't see it. So we need to observe lots of planets for lots of time to try and detect this. And that's the challenge that's been facing planetary radio astronomy for the last few years. And here's our solution. All the sky, all the time, the Owens Valley LWA. What we're doing is we've combined, basically there were two projects. I'm trying to detect hot Jupiters. This is the hot Jupiter detection experiment. Hey Jude, my postdoc was a Beatles fan. And then I got talking to a gentleman in Harvard who also was very interested in low-frequency astronomy. But his project was cosmology, trying to detect the dawn of galaxies after the Big Bang. What we both realized was that our projects were very complementary. He was trying to build a system that images all the sky all the time, which would be the most powerful radio camera yet developed. It actually used GPUs as its main power for basically multiplying the signal from various telescopes. And that allows you to basically combine very large numbers of small telescopes rather than small numbers of large telescopes. What's the advantage? You have the same collecting area, but suddenly rather than seeing a small part of the sky, you see a much larger part of the sky. In our case, we want to image the entire sky. And this system was perfect for planets. The most powerful radio camera yet developed. We didn't have a home. And we developed a concept of building a new array in Owens Valley. So here we have the Owens Valley floor. These are the two dishes I showed you for the Starburst program. This is a 40-meter dish, and this is that VLBA antenna, part of the large array right across the US. We realized if we built an array, especially for this LIDA camera, which had 256 antennas right in one area, we could image the entire sky every second. However, there was a problem. We only had 6 months to basically get funded because LIDA needed a home. And we didn't have any funding. That all changed when Deborah Kassman and Harold Rosen came to Owens Valley in June 2012. And it was a wonderful visit. We visited every telescope, including climbing the 40-meter. This is the largest telescope on site, and this is Deborah at the top of it. And I'm taking a photograph where I'm terrified below her. But she wasn't scared. And it was a great visit. And soon thereafter, Deborah and Harold decided they wanted to get involved with the project. And it really snowballed from there. With their contribution, Top Sofer and Ed Stolper and the directors at the Observatory, John Carpenter and Tony Reed, were able to get the critical mass to fund the project such that we could build it within record time. And that really, for me, is a real example of how Caltech is unique. You can get things done with the right critical mass on a very short time scale. And that's why it's just fantastic to be here. So soon thereafter, we started doing site surveys with our equipment to find where is a good site. Most importantly, we needed to find a site where you had no radio frequency interference, no power lines, no microwaves, all kinds of contaminants for our data. Turns out, right down the valley floor is pretty clean. Here you have the AM band and the FM band, and we wanted to be right in between the two, and it's actually pretty clean. We got through all the process of making sure the environmental issues were taken care of. There were no cultural impact issues or no rare species of fauna that were there, and those problems are very limited, allowing us to commence construction in January of 2013. So we had on-site, suddenly arriving, 88,000 meters of cable, 1,000-meter of fencing. We had to trench 5 kilometers, and we had to start all this antenna assembly and installation. It was a huge construction effort, and it was the Owens Valley staff that led the way. I learned very fast when it comes to this kind of work. I'm incompetent, and happily they are not. Here's how they figured out to actually lay the cable. We had to put down 88,000 meter of cable and put it down simultaneously in these trenches. And obviously problems occur because the soil is quite dry, it can fall in and so on. And they built this contraption here to enable the process. And that's one example of how they just blew me away. We finally showed up after they'd done all the hard work to build antennas in March of 2013, including 4 students who were doing thesis work on the project. Here's our first antenna built on March 8th. We had some dust storms soon after, but after the first day, we got down to serious work. It turns out you can build them pretty fast. 3 antennas can be built in 50 minutes. We had 3 teams of 3 of students competing to build antennas. We had, and I should mention that even though they take a very small amount of time to build, they're pretty robust. Here's Kunal standing on one. So we basically had a competition to try and build them the fastest. Probably not a good idea for quality control, but we got things done. They competed over the weekend to try and build, and they labeled each antenna with their names. So here's the first up is the A team, Team Dinosaur. I don't know where the names came from. They had one student with an injury, so they got an extra person. And then we had Team Tornado, and Team Dinosaur won, incidentally. So here's where everything went. All the cables came back to our electronics shelter in these pipes here. And this is probably what I think is the most impressive aspect of the entire array, because an engineer on site, Russ Keeney, built this incredible container that basically holds our camera, but also holds our pulsing planet finder, and I'll discuss that in a minute. But that's a lot of heat within that container. And he built this huge HVAC unit to basically get rid of all that heat. So we can actually put about 50 kilowatts of electronics inside that one container. Here are 2 of the students who are doing their PhD with the array, and they spend, I think, 3 full days just cabling up. So they've really earned their data, I think. And here it is now today, fully cabled up and operational. And this is the largest number of antennas ever brought together and combined in this fashion. The other big thing that we have in there is our pulsing planet finder. Developed in collaboration with JPL, led by my colleague Joe Lazio, who's here in the audience. This is a big, beefy computer that uses GPUs once again to allow us combine all those data from every small telescope and image the entire sky every second. So rather than trying to observe one planet for 40 hours, another planet for 40 hours, we observe them all at the same time. And that's how we're going to beat that problem. This radio transient monitor has just been finished construction in Caltech, and it will ship in about 3 weeks to Owens Valley. So here now is the new valley floor after construction. And in this area right here, we have the array. We'll zoom in here, and we see all these little white boxes, our antennas. I was very lucky that Google decided to produce imagery just the day, within days of when we finished, because we hadn't quite finished, but we had all the antennas built. And here's our side view now. Now we have this array that's basically on the valley floor. It has a combined collecting area of about 5 times of those dishes. But instead of having a small pencil beam on the sky, it sees the entire sky at once. Here's our very first image, just made with 2 seconds of data very crudely. That's the horizon right here. Here's the galaxy, and here are a couple of the brightest sources in the sky, Sig and Cassay. So I want to thank Deborah and Harold again for making this happen on such short timescales, because I really didn't think it could happen so fast. Right now, we're upgrading the array, even though it's just finished. We're building 32 more antennas. And this is the LWA high-resolution expansion that Deborah and Harold just funded that basically allows us to improve the resolution of our camera by a factor of 10. So here's the former beam size. Now we'll have a resolution of this. This image will improve by 10 times the resolution in about 4 months. And we're moving in technology. Rather than using coaxial cable like we did before, we're now using optical fiber, and that's been developed by Sandy Weinreb, based here at Caltech. He's developed the capability to allow us to use optical fiber rather than coaxial cable, and that makes it much easier to go out to long distances and larger arrays. And we're also using solar panels to basically power the antennas. All right, last slide. I wanted to say that the future. This is the first step. We're trying to build a much larger array called the Cosmic Dawn Array. This is a project funded by the Caltech and JPL President Directors Fund. Right now, we're doing technology development to try and develop the ability to build a much larger array. And we're going into completely uncharted territory because we're trying to combine 2,000 dipoles. To give you an idea how difficult that is, the VLA has 351 baselines. Our Owens Valley array has 35,000. And this will have millions. So that's how challenging it is to process the data. Currently, we're producing a gigabyte of data every second. And this will produce a terabyte. But it will be the most powerful radio telescope built at low frequencies. And it will have 100 times more data than any array. But it's using new technology, solar-powered antennas, optical fiber network, and advanced DSP technology. And it'll do cosmology. But more importantly, I think, for me, it's going to go after planets like Jupiter-sized planets at greater distances from their host star. And I will stop there.